Assalamualaikum warahmatullahi wabarakatuh. So for this video, we will do a question related to rivet, tutorial number 2 from past year 2010, question number 2. Let's read the question. A bracket in the form of plate is fitted to a column by means of 4 rivets A, B, C and D in the same vertical line. So this is vertical line. As shown in figure below, a load of 100 kN is applied to the bracket, which is horizontal distance about 150 mm from point E. The load acts on angle of 30. So the load acting on angle 30 to the horizontal. The rivets are made from steel having a yield stress of shear 240 megapascal. So this is the yield shear strength 240 megapascal. Take the factor of safety. So this is our end factor of safety of 1.5. Determine the resultant load at rivet A and D, and then find the maximum diameter of rivet. So now let's write all the information given from the question. So now let's find question A, which is to find the resultant force at rivet A and resultant force at rivet D. Now let's assume rivet D as the reference point. Let's draw the configuration of the rivet. So point A, rivet B, rivet C, and then rivet D. So the distance between rivet A and B and C and C and D is 60 millimeter vertically. So take D as a reference point. Now let's find the coordinate of X for centroid. So summation of area for the rivet times the distance between the rivet to the points of our reference, which is rivet D, divided by total of area for all of the rivet A, B, C and D. So rivet A, and then for the rivet B, then for rivet C, plus for rivet D, divided by total area of all rivet A plus rivet B plus rivet C plus rivet D. Let's assume that cross-sectional area for rivet A, B, C and D is all the same, so we can assume all of them to A. So coordinates for X bar, which is for the centroid on the x-axis, is equal to A XA plus XB plus XC plus XD, and then divided by 4A, and A can be cancelled out. So distance on x-axis from point A to point D is 0, B to D also 0, C to D also 0, and then D to D 0. So 0 divided by 4 is equal to 0 mm. So coordinate for X bar for that centroid on x-axis is equal to 0 millimeter. So now let's find coordinate Y bar for centroid on y-axis. So Y bar is equal to summation of area for that rivet times this distance between the rivet to the point of D in terms of Y direction, and then divided by total area for all rivet. So Y bar is equal to area for rivet A times the YA, and then for rivet B, and for rivet C, last for rivet D, and then divided by cross-sectional area for rivet A, B, C, and D. So now let's assume that cross-sectional area for A, rivet B, rivet C, and rivet D is all the same with A. So y bar is equal to A times with total of distance YA, YB, YC, and YD divided by 4A. So area A can be cancelled out. So YA is 180 plus YB 120, YC 60, and YD 0 divided by 4. So we get y bar is equal to 90 millimeter. So the centroid for this type of rivet configuration is located at centroid 0, 90. Now let's draw free body diagram for that configuration of rivet. So we have 4 rivet A, B, C, and D. So our centroid here 0, 90, and distance between rivet A and B 60 mm, B and C 60 mm, C and D 60 mm. Next, distance between centroid to point D is 90 mm, and distance between point A to centroid we assume is RA, and then rivet B to centroid RB, rivet C to centroid RC, and then rivet D to centroid RD. And we know that there is applied load of 100 kN acting with angle of 30 degree. Given that the distance between applied load 100 kN to centroid is 150 mm. Next, we need to find the length value of eccentricity between load and centroid, and then the rule of thumb is the line of action for the applied load and centroid must be 90 degree. Then for each rivet we'll have direct shear force acting opposite with the direction of applied force. So we have BA, BB, BC, and BD. Next, because of the eccentricity factor, which the applied force does not pass through the centroid, so there will be an applied moment acting on centroid, which applied moment M is equal to applied force P times with the eccentricity length E. Then for each rivet there will be a resisting moment acting opposite with the applied moment. So resisting moment at rivet D, MD, is equal to FTD times with RD. Then resisting moment at rivet C, which is MC, is equal to FTC times with RC. Then we have resisting moment at rivet B, which is MB, is equal to FTB times with RB. Then for rivet A, we have resisting moment acting at rivet A, which is MA, is equal to FTA times with RA. Now, after we have identified the direction of resisting moment for every rivet, now we can determine the direction of tangential force for each rivet. The tangential force must be perpendicular with the distance from rivet to centroid. For rivet A, the direction of tangential force is acting to the left, follow with the direction of resisting moment for rivet A. So this is our direction for tangential force at rivet A. To the left, FTA. Next, we will determine the direction of tangential force for rivet D. So for rivet D, the tangential force will acting on the right side, which follow the direction of resisting moment at rivet D on clockwise. So this is our direction of tangential force for rivet D, FTD. So in order to find the eccentricity value E, we need to draw the triangle between centroid and the point of applied force. So this is our centroid, and then this is the eccentricity line E, and perpendicular to it we have the line of action for applied force 100, and then the direction of applied force to the horizontal line, we have angle of 30 degree. And then the value from centroid to the applied load, so we have 150 millimeter. From sine rule, so sine 30 degree is equal to E divided by 150 millimeter. So simplify, we get the value of E is 75 millimeter. So applied moment M is equal to P times E, where M is equal to P 100 kilonewton and E 0.075 meter. Simplify, we can get applied moment is equal to 7.5 kilonewton meter. Known that RA is equal to 90 millimeter, RB is equal to 30 millimeter, RC is equal to 30 millimeter, and RD is equal to 90 millimeter. For direct shear force for each rivet, V is equal to P divided by number of rivet, where P is equal to 100 kilonewton divided by 4 rivet, so equal to 25 kilonewton. Next, for tangential force for each rivet is equal to tangential force for any rivet is equal to moment times with the radius between rivet to centroid for any rivet divided by summation of radius square for total rivet. So tangential force for rivet A, FTA, is equal to moment times with the RA divided by RA square plus RB square plus RC square plus RD square. So tangential force at rivet A, FTA, is equal to moment 7.5 kilonewton meter times with the RA 90 millimeter divided by RA square, so 90 millimeter square, plus RB square 30 millimeter square, plus RC, so 30 millimeter square, plus RD 90 millimeter square. So at the end, we get the value of FTA is equal to 37.5 kilonewton. Next, for others tangential force, we will use the ratio method where FTA divided by RA is equal to FTB divided by RB is equal to FTC divided by RC is equal to FTD divided by RD. So 37.5 kilonewton divided by RA, which is 90 mm, is equal to FTB divided by 30 mm for RB is equal to FTC divided by 30 mm for RC is equal to FTD divided by 90 mm for RD. So simplify, we get FTB is equal to FTC is equal to 12.5 kilonewton. For FTD is equal to FTA is equal to 37.5 kilonewton. For rivet A to centroid, so the RA is 90 mm, and then we have applied load acting on centroid, so P is equal to 100 kilonewton at 30 degree angle, and then we have resisting shear force acting opposite with the applied force, which is VA with angle of 30 degree, and then we have applied moment acting at center also, which is F is equal to PE, and then we have resisting moment at rivet A, MA is equal to FTA times with RA. So the direction of tangential force at rivet A is acting on the left, so this is our FTA, tangential force at rivet A. When we see the direction of direct shear force at rivet A, it has an inclined angle of 30 degrees. So we need to resolve direct shear force VA into X and Y component. So this is the X component for VA. So VA cos 30 degree. Then this is the direction of Y component upwards. So VA sin 30 degree. So resultant force acting on rivet A is equal to RA, where resultant force on X axis square plus with resultant force at rivet A on Y axis square, and then we square root. So there is two force acting on X direction, which is to the left is tangential force FTA, and then to the right is direct shear force VA cos 30 degree square, and then plus with forces on the Y direction, which is only VA sin 30 degrees square. So square root all, then we put the value. So FTA is equal to, so negative 37.5 kilo plus with VA, our direct shear force, which is 25 kilo times with the cos 30 degree square plus forces on the Y direction, which is VA, so 35 kilo times with this sin 30 degree square, and then square root. So at the end we get RA is equal to 20.185 kilonewton. Next, we'll find the resultant force at rivet D. So this is our centroid, and then this is our rivet D. So distance between centroid and rivet D is 90 mm RD. And then we have applied force acting on centroid, which is P is equal to 100 kN with an angle of 30 degree. And then at rivet D we have shear force acting opposite with the applied force with an angle of 30 degree. So this is dVd. And then at centroid we have applied moment, which is MPa acting on clockwise. At rivet D we have resisting moment, which is MD to FTD times with RT. So we can assume the direction of tangential force for rivet D is on the right side. So this is our FTD perpendicular with the RD. So resultant force at rivet D, RD is equal to RD on X square plus RD on Y square root. But first we need to result the VD into Y and X component. So on Y component is VD sin 30, and then on X component is VD cos 30 degree. So on X component we have VD cos 30 plus FTD square, and then on Y component we have VD sin 30 degree square, so square root. Next we put the value. So VD is equal to 25 kN times with the cos 30 degree plus FTD, which is the value is 37.5 kN, so square, plus VD, which is 25 kN times with the sin 30 degree for Y component, so square root. So at the end we can get the value of RD is 60.457 kN. So maximum resultant force is acting at rivet D. Knowing that the yield strength SY is equal to the shear yield strength SYS divided by 2. So maximum shearing stress is equal to SY over N, where SY can be converted to SYS over 2 over N. So SYS is 240 megapascal divided by 2 times with factor of safety 1.5. So at the end we can get maximum shear stress is 80 megapascal. So we know that maximum shear stress can be formulated as maximum force divided by area. So maximum force is the maximum resultant force divided by area of rivet, which is pi d square over 4. So simplify 80 megapascal for maximum shearing stress is equal to 60.457 kN for maximum resultant force at rivet divided by pi d square over 4. So simplify again, we can get the maximum diameter for rivet is 0.031 meter or 31 millimeter.